Okay, hi everyone. Good afternoon. Welcome to the last seminar of the semester. Yes, you get a break for about a month, or 2 months after that. For our last talk this semester, we're very happy to have Stefano Recanatesi here from the Technion. Stefano is assistant professor and is heading the Neuro AI lab at the Technion. He did his PhD with Richard Sodix at Weizmann. Then he moved to do a postdoc at Washington University. He was a Schwartz Fellow there, and he worked with Eric Shear Brown. He works on the intersection of neuroscience and machine learning, on Neuro AI, building theory and models for neurodynamics, computation, and representation geometry, and using them to explain behaviors observed in the brain. Some recent works include showing how learning to predict can yield representations that are low dimensional in Latin variables, and linking variables of timing to neural metastable attractors in networks. And today we're going to hear about discrete geometry in neuropopulation. Thank you.
Too kind. Thank you, John. Too kind. Don't give me the long. I feel a foreigner when you introduce me in the long way. All right, nice to be here. I didn't know it was the last one. Hopefully it will close in a good way. Today we're going to have a more theoretical-minded talk. My lab, as he said, is interested in the intersection of biological and artificial intelligence. And the way we think of it is really that there is a synergy there to be unpacked. And we do this, we try to unpack this synergy with theoretical and computational methods. And we use approaches that are mostly borrowed to what nowadays we call representation geometry, so understanding representations in learning systems. I opened my lab a year and a half ago, so I'm still new to some degree. And the current research directions are predictive coding and biologically plausible learning. reinforcement learning. We had an opportunity that was amazing. As soon as I arrived, I got the possibility to perform experiments on humans implanted with intracranial recordings at Rambam at the hospital in Haifa. And we now have a setup with virtual reality and experiments that we can perform. And our hope is to close the loop and do virtual reality closed loop on humans in maybe a year or two. It's one of the dreams when you become a professor that you can have, and then maybe that will not happen, but it's really what we're trying to make happen. And another big theme for us is neuromodulators and one-dimensional control. We're getting some of the first data on co-recordings between neuromodulators and electrophysiology. Here you have the example of neurons that are projecting from locus ceruleus to the brain, and you see, and locus ceruleus, for who is not familiar with, releases noradrenaline, and you can see how these neurons like cast so many projections across the entire brain. Like 30 neurons are enough to span control over the entire brain from one of the tiniest areas in the brain. And so these are data from the Allen Institute, not doing this. But we're really excited about understanding how this kind of control, that we think of it in terms of low dimensionality, can really be one of the leading ways that the brain computes. Today I'm gonna give you stories that have nothing to do with either of this. I'm gonna give you some thinking on what does it mean that a neural representation of a discrete kind of structure. Why is that fair to say, and what does it mean? So let me introduce some of neural recordings. Today we'll work only on recordings that are electrophysiology, neuropixels. And this is an example. So there is a mouse that is implanted with 6 neuropixel probes. These again are data from the Allen Institute for Neuroscience. I spent my last 2 years as a postdoc there, so I still have a lot of data to work through. And the 6 probes here are put together, one on top of the other with different colors, and the implant is in the visual cortex of the mouse. Can you hear me all right? Yes? Yeah. Don't fall asleep. Dimmer light, but attention on me. Okay, so one thing that I hope you can see here, despite the quality is not the highest, is that there is a point where in this neural activity, the animal is not doing anything. Spontaneous activity, just seeing a gray screen, changes. And if you look carefully at neural activity, this is always the case. Neural activity always unfolds in multiple ongoing states with changes that occur many, many times. There are techniques that are unsupervised to identify these neural states, as I call them. And if you apply one of these techniques that is called the Markov model, when if you are familiar with this, you would be able to parse each of the probe, 6 lines and 6 colors up there, in terms of states. So the green state says that the neural activity here is rather stationary, and then the algorithm would tell you, well, there is something happening here, and then it goes back to the same state. And as you see, because you have 6 rows that are saying pretty much the same stuff, it means that this is happening simultaneously across the entire visual cortex. As we know, these states are influenced by behavior. So if you look at the pupil or the speed, we do see that the pupil is changing when there is such a change. Let me see. And if you inspect a lot of neural activity, as I was mentioning before, you can really try to think as this unfolding activity over time, where, for example, when the animal stops and doesn't move, one state, this red one appears, and then the pupil would climb up and then decline, and you would still have this unfolding of states. And the only thing I want you to bring home from this animation is that neural activity comes in packets. I don't want to convince you that it comes only in packets, but I want to say that there are sudden changes where the activity changes, changes. And these changes can be more or less sudden, but I think to some degree they're undeniable, that you can think of it in terms of packets or neural states. So if I am to take these colors, identified again by the Markov model, and put them in a table up there, where each row is a minute of activity, so you have 30 minutes of activity and I'm only expressing the color, so the identity of the state, then you can see that the colors unfold over time, and they return. And for example, the red color over there is when the animal is not moving. And if you look at, and you can take this representation and look at it across multiple areas. In this case, we're all in the visual cortex, so there is some variability, but not too high. And as I mentioned before, this is strongly correlated with the pupil and running, with behavioral variables. Nothing new, so we're just putting data up front. Here's where the twist kind of starts. When you start having so many data, and we're not talking too much, but still, say 1,000 neurons, you can take each area and think of it in a different way. You can say that this is a vector in population space, and you embed it in the high-dimensional space of neural activity, and you think of the representation as a point cloud representation. Each dot there in this cloud is a moment in time of the neural activity. Again, they're familiar with this. But this change, right, of representation from raster plot to point cloud allows us to ask questions that before we wouldn't ask. That if you had 10 neurons, you couldn't really see this point cloud. But when you have 1,000, then you can say, what is the geometry of this thing? What is this thing? What is the green and red? What is the difference between two states? Is one bigger than the other? Are they aligned? Are they in a high dimensional space, low dimensional space? What is the difference of green across areas? And these are the kind of questions that we ask. This is what we call kind of neural geometry approach, because we ask questions about the representations from this kind of Iber type, however you say. And the idea of neural state comes also at hand because it's sort of a discrete object. So if you think of each of these states as a point in one space, to simplify, right, you take these clouds and you say, well, they're just one point for now. Then one of the questions that is legitimate to ask is, are they embedded in what kind of geometry? Is there some sort of semi-low dimensional geometry that captures them? What is the dynamic between these states? Is it repeatable? Is it always a sequence? Are they embedded in a flatter geometry, in a high dimensional geometry? Does it look like more noise or flat or what? So the whole point of the talk is that neural states can be thought as discrete controllable units of computation. And what I'll try to show you, not to convince you really, but to give you an idea of why this perspective can be interesting, is the fact that there are some advantages when you perform computation with this kind of units.
Maybe I'm trying to understand if this claim, this is your assumption or this is your conclusion?
It's both. I think it's more of a prior. Okay, I think that's how we should call it. As I said, I guess what you're saying is that you're cheating here. You're telling me that this is discrete, but it's really not. It's continuous at times, more discrete at others. And how do I decide is not clear. Is this something that we need to prove, and so we prove it hardly, and then it's a conclusion, or is this something that you cannot prove, so it's just an assumption? And at times you can prove it more. We did a lot of analysis, we did the Markov models, and we're developing new tools that are more sophisticated. Like, for example, there are SLDS, which in linear dynamical system, where each state has its own dynamical system, and then you try to pull apart. And we did comparison between GPFAs, like Gaussian process factor analysis, and did the Markov models to tell which areas are more or less identifiable with this assumption. In the end, it's hard. And the answer is both. There is this discrete nature, but it doesn't explain on neural activity for most areas. And it mostly works in the cortex. It doesn't really work so well in other areas, like hippocampus.
I'm a bit confused about the correspondence between the neural activity and behavior. Because on one hand, you said that, and we see in this example, that the nice correspondence between the state transition and the behavior. But on the other hand, you said that different brain regions exhibit different correspondence. So kind of confused about that.
Thank you. Let me get to you in 2 slides.
Sure.
Fair? Because I have a better figure in 2 slides. Okay, so here's what we're going to do in the next half an hour. I have 45 minutes. So the first part, I'll try to show you that there is an advantage in computing with states of a computational nature. And I'm gonna explain this idea of a sensitive regime and what does it mean. And in the other part, I'm gonna show you that there is some sort of learning that you can do when you think in with discrete objects that also you wouldn't think of if you were doing it with continuous representation. Both ideas are simple, and this is gonna be all the talk. Okay? Two simple ideas related to discrete geometry. 1, 2.
So just to understand the assumption, so the assumption that the neural activity is discrete, so you're looking at the prototypical vector for each state and you assume the rest is noise around it, or?
Yeah. Let's say that is the simplifying assumption here. So instead of thinking of neural activity as a Gaussian process of a continuous trajectory that unfolds in time mostly at the same speed, you think of more of it as a point process where the activity is stationary for a long time and then it jumps. So pseudo-stationary, so noise around, or small dynamic, slower dynamics, and then jump.
And that's Markovian transition between.
Well, that's a bigger question. But you can think of it in the Eden-Markov model fits, it's Markovian. Yeah. Whether neural activity is Markovian or not, I don't think so, but that's the assumption under behind the Eden-Markov models. Okay, so this is the same figure, similar. Okay.
So
Last question for now, then I'll keep going for it.
are we talking about the Markov state as including the population or for a single neuron?
No, this is a population thing. So here you feed the state as an entire population. So here in this figure, right, is the same. We take neural activity, same recordings, the color change, but it's the same recordings. You infer the state, and here the state is now inferred over all the neurons at once.
So it's
Yeah,
not
neurons.
just the change in firing rate.
Yes. We're developing more sophisticated models to do state inference, but this model is very simple. Each state has a specific activity for each neuron. So if you have 300 neurons, you have 300 average activities, and then you assume a specific noise around, which can be Poisson, for example. So you use central activity, it's called emission, and then Poisson noise on top, and that's your state under the Markov model assumption. Animal speed, whenever you see that the animal speed increases, you see that the activity changes. This we know from many works now, it's very common. And you see, if I do my table of states each row a minute, I would see that the light yellow corresponds to speed. So whenever the animal is moving, like in red here, I would see the yellow here. It doesn't mean that the activity is fully stationary, but it does mean that you are at a different operating point of the activity. And if I do again the representation in terms of point clouds, I would see something like this. This is very common. For whoever does a PCA on at least 80 neurons sees these exact figures, colored in different ways. If I now remove the top two components that are shared across all neurons, I perform what is called factor analysis, and I remove two components, I would see this structure. Okay? So it's not that the state structure is not there when you perform in PCA, it's just that it's hidden under some common top principal components or factor component.
So I just wasn't completely clear. So the states are defined by algorithm over the neural activity, like Markov, or over the behavior? How do you define that?
Over the activity and only the activity. There is no
so
behavior.
you correlate later to the behavior.
Correct. Thank you for asking. Only the activity. Let's ask a few questions about these states. We have half an hour of recordings over about 50 animals. And we start by asking what is the dimensionality, a common question these days. What is the dimensionality of each of these states? A common measure of dimensionality is called participation ratio. And if you take the eigenvalues of the covariance matrix, which are how much of variance is explained over each principal components of your activity, then you can pack it in this way. And you come up with a measure of dimensionality that tells you that exactly what you think, that if something is like a sphere, then it would be fully dimensional, but if it's more like an ellipsoid in one dimension, then it's closer to dimension 1. And here we do it across states, and we get that the representation is pretty low dimensional. I will explain better what I mean with low in a second. And we do it within each state. And within each state, you have more symmetry and a higher dimensionality, but it's higher. But the crucial point is that it's still relatively low compared to the number of neurons that you have.
Could you elaborate on what exactly you mean by the dimensionality across states and within states? Like, how do you measure that?
Yes, thank you. Across states, you take all the neural activity and you perform PCA. You get your eigenvalues, you put them in the metric, and that's what you find.
Just the full
thing.
ratio.
Here, you focus on a single state. Whenever activity in time was in that specific state, you take only those points, you do that dimensionality, and you get that metric.
And what does it mean for it to be larger when you're in a single state?
The fact that it's larger is something that, here it could go both ways, okay? It could be that the orange bar is above or below. And to be honest, I don't know where it would go if I would be in other conditions. Because here are, for example, 8 states. There are not so many to span a very high dimensional kind of representation. If I were to drive my visual cortex with 1,000 images, then I might expect that orange bar to climb up, and then each state to be lower. And I don't have the answer for you, I didn't do that analysis, but that's where the literature, for example, Carandini-Harris have this paper, High Dimensional Geometry of Visual Cortex, that drives the activity with many images, and that bar is supposed to be much higher. He has a follow-up question.
Yeah, sorry, so really, what would you say about the computation through time based on the difference here?
What this is saying essentially is that if you do PCA over all your activity and your activity is jumping around across states, most of that variance is explained by the transitions between states. That's what these two bars are saying. If you remove those transitions and you just focus in one state, then the dimensionality all of a sudden is completely different, because most of your variance is gone just for transitioning from one state to the other, because these are further apart than when you stay in one. That's what you get from these two bars.
I think you get these results anytime that the separation between clusters is much larger than the size of the cluster. It doesn't mean that the cluster needs to sequence some lower dimensional memory.
Correct. That's it. You said in a much better way what I just said with more words. Yeah, this is not surprising. Yeah. But we wanted to understand how we can put a number here. This axis is very confusing. When you have all recordings that are from different animals with different number of neurons, how do you normalize that axis? This metric is non-linear. If you just divide by the number of neurons, you're not doing the right thing. If you have 10 neurons and then another recording with 1,000, you can't put it on the same axis. It's just wrong. So we looked at the metric more in depth, and we realized that in the metric there are 3 numbers really that matter. One is the standard deviation of autocovariances, the diagonal of the covariance matrix divided by the average. One, the standard deviation of cross covariances, of diagonal elements of the covariance, and then the average of cross covariances. These are 3 numbers. I'm not explaining in detail, but there are 3 numbers that you can estimate independently. There is a bias when you do this estimation that you need to remove. It's all in the paper. This is all there. You can find the details. And then you can, at that point, extrapolate with n, where n is the number of neurons that you're recording. So you can put everything on the same scale by fitting these 3 numbers and say, I pick n to be 1,000 or 10,000. And this is what we did. We started with 300 neurons. We estimated these 3 numbers, and then we extrapolated to 10,000 neurons. And so let's just set a very high number of neurons. That's our reference. Let's say that we work with 1,000 or 10,000, and eventually we set on 10,000. And the reviewers came to us and said, well, this is wrong. You cannot think of estimating these 3 variables from 300 neurons and say that this is the right thing when you go to 10,000. You have plenty of biases here, and you're probably doing some mistake. So we're like, okay, we will record more neurons. We went back to our collaborators in Jülich, Simon Musal, and we asked him, can you record 10,000 neurons for us? I was like, oh, here we are, 3 months later. We reapplied our technique. We started from 300 neurons, computed our variables, extrapolated to 10,000, and it was actually reasonable. It worked. Completely different data, were calcium and electrophysiology, but the technique kind of worked. So there is a way that we developed, not too complicated, but also not too simple, there are multiple stages, to estimate dimensionality across recordings and just put them on the same graph. And then we realized that if this line is indeed right, it's saying to us something non-trivial. That is that the network is really low dimensional. Each state has really less degrees of freedom or dimensionality than the number of variables that it has, the number of neurons. So if we were to try to reproduce this kind of activity with a model, with a recurrent neural network, it turns out that in order to replicate this kind of result, this sort of saturating dimensionality for each state, you need a very strong recurrent network. If the network is weakly recurrent, then this would keep climbing. But if the network is strongly recurrent, this would saturate. And yes.
Why the dimensionality in the calcium imaging so different from that of the physiology?
Interesting, right? Yeah. Are you asking why this curve climbs up more?
So much more.
Yeah, it does. I don't know. I think there are many reasons. One, it could be that we are mistaken, right? It could be that if we record 10,000 neurons with electrophysiology, this climbs more. It could be that we're still wrong. It could be that when you record with calcium imaging, you're off to record a different signal that is more correlated on neurons because you record more bursty activity, say. And maybe bursts are more correlated than regular activity. Or it could be your favorite explanation. I don't have an answer.
It probably would be dependent on the task as well, right? What Simon did they do the same task that you built the model on?
This was spontaneous activity.
This was that was spontaneous, right?
They're all spontaneous.
They're all spontaneous activities?
Yeah.
So it's
What's the volume?
Well, here you're 6 neuropixels, so you're in the volume of visual cortex. These are the 6 areas that are neighboring. Here it's, well, this is pretty big field of view, so it might be that that's the best explanation. I don't feel like I can claim I know the reason. Maybe I should go back to Simon and ask. But the point rests, okay? Independently, if you look on the left or you look on the right, these numbers are different, but they point, I think, to something that suggests that there is a principle behind that if you see a very low dimensional recording, there are a few things that it can be due to, but one of these is the fact that the network generating this recording is strongly recurrent. From a theoretical perspective, there is a one-to-one relationship between recurrency, the strength of the recurrency in the system, the strength of the synapses, or the amount of recurrences. I will quantify this more in 5 minutes. And the dimensionality, intended as participation ratio divided by neurons. So that if you do it in spiking network in different ways or in mean field, you always find that there is this one-to-one correspondence.
Why can't this be due to a low-dimensional feed-forward signal?
Correct point. You're leading up to 10 minutes from now, hopefully. Forget it. The thing that is really missing from here, as Jonathan is saying, is the fact that the input induces also some variability, and this model is neglecting it, and that's what we are doing now. We're accounting for the input, which is not in this picture. But even if you account for it, which we did in the control of this paper, then it remains true that neural activity, at least as we are recording it now, sits at this point, at the bottom of this plot. So that the neural dimensionality is very low, suggesting that you're here, in a very strongly recurrent region. And the point of that regime, at least the way we understand it for now, is that the advantage of being here and not here, say, is that when you are this far in the plot with strong recurrency, if you change a bit this one, you have a very hefty change in dimensionality. So if you look at the delta R, so you change dimensionality just at 5%, sorry, you change recurrency just 5% wherever you are, then the change in dimensionality is much higher when you're here. Just the derivative, okay? Nothing more than the derivative of that plot. It's a trivial mathematical fact, but it's an important, I think, deep potential mechanism, because it says that if you do want to tune the dimensionality or complexity of a representation to some computational demand, then you're better off start with a strong recurrency so that you can tune it fast. Otherwise, you need to move a lot in your scene. So this is to open up the relative dimensionality as a function of areas or layers. We do see a significant difference where primary visual cortex is lower dimensional than other areas, and similarly layer 2-3, which is believed to be more recurrent, is lower dimensional. And under the idea that I just mentioned, that the advantage is that if you're strongly recurrent, you can modulate your dimensionality more, then it follows to some degree that each state might have a different dimensionality footprint, because it can be more controlled. So we went and did the following analysis. We checked whether or not, whenever we change state, the dimensionality of one state to the next will change a lot. So we had that essentially whenever we move from one state to the next, we have a dimensionality change of about 50 to 100%, so twofold increase. And this is true both again across areas or layers. And if you are to repeat the same analysis on packets of activity of the same state, then you see that the change is lower, which you expect in a way because you parse the activity within the Markov models, but still it's an important bar, right? So what we are saying here is that there is something here that I want you to take on. If you are computing with discrete states that are all relatively low dimensional, then whenever you do this sudden transition from one packet of activity to the other, you might be exploiting a different computational unit. And these computational units are quite diverse in their geometrical properties, or at least they can be. So that you can change all of a sudden the amount of variance and dimensionality and degrees of freedom of your system from 1 millisecond to the next step. And you cannot really do this if you weren't using these discrete units. So we call this sensitive regime. Why is we gave it this name? Might not be effective, but I think it captures something. And it captures the fact that dimensionality is sensitive to the underlying recurrence. And we try to understand more in detail what does it mean to be sensitive to the underlying recurrence features. And we unpack the theory a bit more to see that. So we started with this simple, it's kind of complicated to compute this plot from a mean field perspective, but this is a simple one-to-one plot that says the dimensionality is lower when you increase the recurrency. And then we unpack this recurrency into our original synaptic strength variable, that is this sigma, and other features that are called motifs, that are synaptic motifs. And they come in 4 kinds that are divergent, convergent, reciprocal, and chain. And this is a theory that Chaim Sumpulinski has also done has achieved very similar results from a different theoretical perspective, but the same formula. Yeah.
Can you just explain what is R from 0 to 1? Everything scales as square root of n, I imagine.
Yes.
So what is from 0 to 1?
These all are from 0 to 1. They're like correlation coefficients and the way they're measured. So they're all normalized to the variance, so they cannot be there between -1. Is that what you're asking? Whether each? Yeah, there are some details obviously that are not present. So we went back to data to try to compute this these factors, essentially the expression of reciprocal, convergent, divergent, and chain motifs. There is a team at the Allen that does synaptic physiology. These are in vitro experiments with the octopatch, where you target 8 cells simultaneously, and then you verify whether or not there are synapses between them. And out of thousands of these slices, we could compute the expression of each of these motifs. We flatten it down to whether or not the neurons that are involved in the motif, there are 2 or 3 to see, but sorry, the synapses in the motif, that there are always 2 synapses. They're both excitatory or excitatory inhibitory or both inhibitory, and the motif expression changes. But the important part here is that these are well-known results, that there is an overexpression of reciprocal motifs, but there is quite a bit of structure in the motifs themselves. They're not random, they're very strongly structured, and they do have the capacity to modulate the overall recurrency. So that if you look just at this part of the equation, this modulator of the overall synaptic strength by the motifs, then you can see that these can be quite different, can be different across layers, and in principle it has the ability to tune the complexity of the recurrency and have an effect potentially on the dimensionality that we were talking about. So one of the results that correlates, but it might just be at random, but it's the kind of stuff that this sort of frameworks bring forward, is that if in layer 2-3 you have a stronger recurrency, which means that this thing is to the right, then the dimensionality in layer 2-3 should be lower in the electrophysiology. In our data, these are 2 different data. This is electrophysiology, this is synaptic physiology. They don't live together. But this is the kind of thing that should remain true if we record at a larger scale. For us, it happened to be true. Maybe we were just lucky. But this is the kind of prediction of the theory. So to bring it home, right? Well, I've been talking a lot, but I'm saying something that I think is intuitive, that when you compute with discrete states, you have a computational advantage, which we call sensitive regime, and it is the following. The neural states allow fast dynamical control, fast change over the representation complexity. And such control can be exerted by the underlying connectivity. Okay. This is a computational advantage. It's an idea. Proven or not, this is an idea. And you can read all of the details in this paper that is on bioarchive and is still under review. I think I'll jump to the second. So here I have another part that is on the inputs, exactly as Jonathan was saying. I have a fantastic postdoc that has been working out the theory for how to modify this equation of a network with the inputs and compute mean field and understand multiple variables. So this is exactly the concern that we had of how whether or not this story is robust to the inputs. But maybe we can talk about it over a beer. Yeah.
So the motifs are kind of a global measure, right? But you have those different fixed points.
Yes.
Are they just by the structure of the network, or are they, you assume that they are the inputs? I mean, how do you get the different attractors?
The different motifs?
The different attractors. Motifs are global, but you still have, you have several states, right? What creates the states?
So as you see, this is kind of weird. I never use the word attractor. And I didn't do it on purpose, in the sense that we do have other work where we think in terms of attractors, and these might be metastable attractors, but they don't have to be for all of this to be true. So this could also be states of recurrent activity that are driven by the input, not metastable, but simply like fixed with correlation on top. And then the idea would be that this is the bottom line of what we're getting here. If you think of early areas like you have a hierarchy in the circuit. The circuit is more complex than just visual primary cortex. Then you would have thalamus, visual cortex, area sensory cortex, midbrain, or other areas. So it might be that the role of the thalamus is to route your network according to one of these specific states. So each state is a trajectory of computation that is an operating point of the network. then because a network has many operating points, many such states, then you can think of the motifs to locally tune their features around these specific points. Because you might have just 40, 50, 100, but each of it could be tuned separately even by the local motifs.
So again, so the motif gives you the stability for each region, but the structure of is something global that comes in your model would come from the input.
Yes. This is a bit more tricky, so it's a bit more technical. Can I have 10 minutes? Are you guys done? You want me to close? I want to give you this other idea. It's also, we published it last year. This is a different idea on essentially how to encode sequences, but sequences of states. And it turns out that when you work with discrete states, like the picture that I gave here, and you transition between them as a sequence, you can encode the entire sequence in a way that is more compact than we thought before. So let me explain what I mean with that. I want to give you two mathematical facts that I find extremely simple, but they're at the core of this idea. And one is the following, that if you have high-dimensional random vectors, because they're random and they're high-dimensional, they're orthogonal. I think we all understand that. And on top of it, if I take some random vectors and I start summing them, and then I take the sum of them, and then I take, which I call M, I take 3, I sum them, I call the sum M. This will be what we call path vector, in the sense that is a path of vectors if we add more and more. And then I multiply these by one of their components. This is one of the simplest feature detectors that you can think of. The scalar product, as we just said, will be 0 if it's not itself, and 1 if it's itself, and normalized accordingly. You're tired of listening to me, but I hope this is clear. And if I do it with a vector that is not in the set, then it's 0. Okay? Why this is true? This is true simply because this thing is, I put in my M a number of discrete elements that is not a morphing from one to the other. I just say you as discrete objects. So I'm doing a set operation. Let's use it to build a learning goal. So if I think of these as activation patterns, each of my random vector that I called R is now an activation pattern. I can think of building a memory trace that simply sums up the activities that I had. Or because I like to think learning in terms of synapses, I take 2 layers and I say that whenever the neurons that are active in one layer, I take that pattern and I increase all of the synapses that come out of the neurons that were active. So I take a set of patterns that build a sequence, I sum them all up, and then I increase the synapses that come out of the neurons that were active. This is very different from Hebbian. Why is it different? Well, in Hebbian, I do something that is usually in most of the versions of Hebbian, pre- and postsynaptic, which means that I look at the activity of the presynaptic, first layer, of the postsynaptic, second layer, and then I increase my synapse only if both of them are active. Here I'm not doing that. Forget about the postsynaptic neuron for simplicity. If I'm active, I potentiate. So it turns out that such a simple rule that looks simply at whether or not when I traverse a sequence of states, here we took the example of a motor sequence of a monkey foraging some food. I take the sequence. This sequence can be thought of being embedded in a layer of representation which is sparse, and this is a critical assumption. This is going to work only if your representations are very sparse. Then I can sum up the patterns of activity, increase my synapses, and build something that is a readout neuron that tells me exactly what I was saying before. Is this pattern something that I've seen before or not? It's part of the sequence. And I can use it then to retrace my sequence. So I will explain these 3 stages a bit more slowly, but still in 5 minutes.
Is there inhibition also?
Here we're taking it very simple. We have an example in the paper where we compare this kind of learning rule, which we call one-factor path vector, that's how we called it, with STDP, and then we have to check the inhibition, and it is a bit the role of inhibition, but here not. In the simplest case, you take a state, you forward it through a K-winner-take-all layer as an example of representation. As long as this is sparse, it works. And then you can take this representation and play with it.
I may have missed something fundamental, but
God.
there is a baseline. If you don't have inhibition, there will be a baseline, and then the vector will not be.
You need to make the weight decays. The neural activity is fixed here. You don't have a model of learning on the neural
You
activity.
need to have approximately zero average activity.
Where here, I will explain more in a second, but here I'm not learning these weights, I'm learning these last weights. So there is no change in the neural activity. The neural activity is just encoder layer, and I'm not learning the encoder. I'm just learning a very simple decoder from these layers to, say, a single neuron that tells me whether or not the pattern is in my sequence. If I keep playing with my rule, those weights will keep increasing, which is a problem, and you can play with weight decrease. But it's not, the activity is fixed in this simple way. Yeah, allow me to explain, to open up these 3 packages quickly, okay? I'm claiming that the setup here is to think of it as states in a behavioral trajectory with a counterpart in the brain, a representation, and then see how we can retrieve the sequence. So I take these different states, and I think of them through, I have a random encoding high-dimensional vector. So each state corresponds to one of these vectors, say state 1, vector 1, state 2, vector 2, and so on. Each of it will have some neural activity, and they say that I just harvest or collect all the neural activity. Say even over 30, 50, 60, 2 minutes. Okay, 2 minutes of activity, say, okay, maybe there is a biological process that can hold the trace of all the neurons that were active. I get to my banana and they say, oh, that's the trajectory that led me to this banana. Burn it in my memory. And I can because I remember the neurons that were active. There is no pre and post. It's just, was this neuron active or not? And I call this M, and in this sense, because I'm harvesting the activity of many representation vector, I call it path vector. Is a vector, is a path in the space of vector representation. Again, if then I take this vector, because of the property of being sparse and high dimensional, I can put many states into it, even 1,000 states, and then ask, was this visited? Was this state part of it or not part of it? And if I take a simple scalar product in this simple high-dimensional space, I can still detect whether or not one of these representations is part of my harvested representation. So
do you have in your network, feed forward of set or just like a network?
This case, feed forward.
So feed forward, each state is a layer.
Yeah. Yeah, it's the simplest you can think of. The simplest case we could have. So in this case, then it should be intuitive on how we can retrieve the sequence. If I start from one of the states, then I can move along the graph, asking whether or not each of my neighbors was encoded in the trace. And I can use it as what we call a familiarity detector, or to verify whether or not I should move forward along one edge or the other. Yeah, go ahead.
And what 2 or 3 neighbors are identified?
So if you visited all of your neighbors before, that would be the case where you don't know where to go. It's true. Or if the trajectories come back and re-intersect, then you wouldn't know how to resolve it. So if you visited all of your neighbors, then it's kind of weird, because how can you take 3 steps at the same time? You will still do it in a trajectory way. And unless you really, you can resolve that case in a reasonable way. Also, intersecting trajectories, you can think of using the momentum if you want, or building a higher dimensional space. We do this in the paper. We resolved all of these issues. And intersecting is really one of the problems.
Now I'm confused by that. You said that the implementation is a feed forward. So why does it matter if you go over the same step again?
Well, because if it is feed forward, it's memoryless. So if it is memoryless, and then let me see if I can bring something down here. Here, right? If I'm here and I do this, I go around and then I intersect again. And when I'm here, I don't know if I should visit first this or this.
Okay, so it is the same layer. You have the same representation of the same layer, and you just have one layer. It's
Yeah.
not to feed forward.
It's a feed forward in the sense that you just use a network to build a sparse representation, just an encoder.
You can also multiply by a scalar, and then the magnitude of the scalar would be the point in the trajectory.
You need the high dimensional sparseness.
Also, yes.
Yeah,
Together.
but there are many ways to do this mathematically, yes. We're not.
Sorry. Am I right to interpret this as permutation invariant? Like,
Yes, in this case, it's you don't have an ordering.
and is that important, or is it?
It can either be a bug or a feature, but in this, like if you think, as Aya was saying, right, you do want to know where you came, you want more of a concept of a trajectory, and there is a way to do it, like discounting the states in time would give you the concept of a trajectory, then the one that you saw last would have a higher discounting, and that would give you a sense of directionality, for example. And this is all stuff that we checked in the paper, for example. Yeah. So we played, for example, we are now showing that this kind of learning, which is really trivial to some degree, but let me close it here, but at least I can give you a couple of comments on this. This sort of learning, the property that is really crucial is that the fact that it's simple, like you take activity and then you say my learning just depends on whether the neurons were active or not. It works only if there are 2 conditions. The world model or graph of states needs to be relatively sparse, and also the activity needs to be sparse. So the high dimensionality and the sparsity is critical for this to work from a technical perspective. But the real advantage is that it's much faster. And it's faster because you don't need as many examples. If you work with STDP, you need the coincidence between neurons, between activities of pre and post, in order to build all of your sequence. And in most of our computational models, you need hundreds of examples before you can learn a reliable trace. Once you learn with STDP, it's fantastic. Because you not only have the sequence, but you have the timing of the sequence. You have all of it. Here, with 10 examples, 20 examples, that is similar to what we see in mice, you can learn a task, but you are not learning the sequentiality of the states, the trajectory, you're just learning the states themselves, but they are not that part of the task. It turns out that this is enough.
I don't see why I'm surprised you moved from unsupervised learning to supervised learning. So supervised learning is easier.
Well,
because you only enforce it if you get the task, if you get it correct, you have an error signal.
Well, but this is true also with STDP in a way. You can think of it in the same way. You can put them on the same ground and say, well.
But you added some external signals that said you got to your goal, right?
Mm-hmm.
That's how you want. So you're in supervised learning. And supervised learning is always faster than unsupervised.
Yeah, but it's not the only reason here. There is also this reason that is really the fact that the number of events that you need when you work with things that are pre and post is much higher because of this coincidence rule. And if you think of learning rules that instead don't require the coincidence event, independently of whether you're supervised or unsupervised, then you scale much faster.
No, supervising just the error in the activity before. We don't need the post-activity for the supervised. Could you just run out? You could imagine that this neuron will detect or fire when it's correct or not firing.
Okay, but then you're not using, yes, you're right, but then you're doing what I'm saying, which is great.
Supervised learning.
Okay, you can call it in different ways, yes. Yes. I understand and agree. So one more thing that we do in the paper, and then I'll close, is that we show that this might be at work in a good place for this to work might be actually the MOSI fibers between dentate gyrus and CA3. And we're also analyzing data of BCI task, where you essentially can close the loop and look at patterns of activity during the task, for simple tasks where the animals learn on these 20 to 30 trials. And we see features of this fast learning that is only activity-based, essentially, and not correlation-driven. And so to conclude, I want to thank you. But nothing. And leave you with these two simple, I think, relatively simple messages. One is the fact that when you work with discrete neural activity, you have two advantages. One is a computational advantage. This is an example of such, that you can change the complexity of the states more suddenly at a faster space, and you can tune it with the recurrence in their line. And that there are learning mechanisms supervised that work in a different way than standard learning rules that you might have seen in a task book like STDP. And these learning rules are really handy when you want to learn tasks faster on the scale of a dozen trials instead of hundreds. Okay. And I invite you to read the papers if you found me too confusing and hand-wavy, and all the details are there and they've already been vetted. Thank you.
We have time for one, maybe two questions.
Yeah, I'm here for you guys. So, a couple of questions. What?
Question. So if I understood correctly, the longer the sequences of sensory inputs, the exponentially more possible states can be encoded.
Why exponentially? Where does the exponentially?
Because exponentially more paths, possible paths are created.
Yeah, okay.
So, if that's the case, then shouldn't the time, longer, let's say a longer sequence of sensory inputs correspond to a higher dimensional neural dynamics?
Yes, I think the answer is yes. The more you harvest time over, the more you get, the more neural population activity you get over longer time scales, the higher the dimensionality. I think the current evidence suggests that the more in sensory systems, visual cortex, or similar, if you drive with stimuli, you expand your neural activity. And the constraints of such expansion, I think, are still to be determined. We still don't know, I would say at large, whether that gain that is driven by input is say exponential or what. There are many questions there to be answered. There are also some papers recently that recorded from a million neurons in the brain from Rockefeller, and claiming that the neural activity is very high dimensional. The more neurons you record, the more it goes up. Again, this is in calcium, and this with a resolution that I still haven't vetted, and I don't know how to say whether or not this is true. It could or could not be true. This is still open. There are still many open questions on the table.
Do you
look at data for regions that know less recurrent, maybe the striatal, for example, and
Or the
test your-
thalamus. Yeah.
and test your theory there.
Yeah, they're completely different in terms of activity patterns. So what I'm showing today is mostly, so for example, let me just go back 1 second to the, I showed these bars and I showed them for visual cortex, right, and multiple areas. And I do have the bars for thalamus, hippocampus, midbrain, completely different stuff. So when you compute this matrix on the thalamus, it's a question whether or not it's working in the same way. Also because it's unclear whether or not the notion of states is there as much as it is in the cortex. And when you fit an DeMarco model to the cortex, it works really well. That you might like it or not, but it works well. When you fit it to the thalamus or hippocampus, it's a much more difficult task. So you lose some of the notions that we have here. So I have been trying to suggest today that using a prior of a discrete states activity on the cortex is a good prior, and that came some way. If I were to do the same in striatum or thalamus, I might have failed.
Okay, thank you very much.
Thank you, guys.
Somewhere, but it's always no.
So we do have, that's the biggest effort at the moment. We do have a theory with inputs, but I only for sure we worked out inputs and outputs. Not easy stuff. I don't know if you guys, you are applying, you guys have similar projects.
I actually have something similar on to ask different question. Who would tell us?
I mean, this is with David. So.
Yes.
I mean,
So I had a student who left after the war, but he was Italian student.
I mean, I'm working.
Let's go outside.
Let me check out that you don't forget. Thanks for the questions.
Yeah, of course. Really cool talk. I really like that. Are you going to have any time today? I assume he's super busy.
He has something at 4 because we have the he has on Gabi's group.
Oh, okay, that's right. Okay.
Yeah, I'm not sure today. I mean, I'm not in 4.
Probably a lot of you.
Oh, we can do that.
Yeah, are you? Are you talking with him after? Is he coming to the lab?
No, I'm meeting him with Gabi.
Okay. Okay, yeah, there was just some, so after we today,
Ah, the NBA sold.
Yeah, which NBA team?
Actually, no.
Really?
No, we like switching. I think that we used to like Oklahoma, but then it was the series of Golden State against
Cavaliers.
yeah, and you got the blood, and you had to choose. So today, I don't know. Last game I was not Oklahoma. Who was in the final? Lost
Oklahoma and
game
Indiana.
7 games Indiana.
Pacers. Yeah.
Wow.
Awesome.
Wow, great basketball.
Do you like the Trailblazers now? Because of
No, no. But I think that I know that everybody likes the coach. I think that the coach is not so good. Like because
Portland?
yeah.
No, I don't know anything about their coach. I just like Danny Avdija.
No, but they got four. I think that if you're taking the lead four players, Sharp, Grant, Avadia, including so all of them, I think they are like the most. If you're taking everything in the US, like four best players, those have the highest like average of like, you know, there are lots of games. All of them have figure points, for example. Or,
Have what?
like over 20 points. If
Oh, yeah?
How call it is?
Double figures.
Double
When you
figures.
have overtime.
Double figures.
Right. Ah, so they're very balanced, is what you're saying.
Yeah.
I'm a Lakers fan.
Even now?
Mm-hmm.
Oh, wow, sorry for him.
So I was a Lakers fan. I'm a fan of one player. There's a guy who plays on the Mavericks now named D'Angelo Russell. Maybe you know him?
Yeah.
He's my,
Wow.
he's my guy.
Wow.
I'm a huge D'Angelo Russell, so I'm a fan of wherever he plays. But he's on the Mavericks.
He
He's
moved
playing.
during the trade of
He was traded for Kevin Durant a few years ago.
Durant.
When Durant went to the Nets,
Yeah.
he was traded. D'Angelo Russell went to play for the Warriors. Durant went to the Nets, and then he got traded during the trade deadline for. I think it was in the. No, I don't remember. But anyways, he's the only player in NBA history to play with LeBron, Steph, and Kobe.
Wow.
Isn't that crazy?
How old is he?
He's not that old. He was a rookie on Kobe's team. He played 1 year with Curry.
Oh, crazy.
Yeah, very cool. So you're gonna prep for your presentation now?
I think I should pass over it.
Good luck. I'm gonna get a coffee. You want coffee?
I would like to if you find someone.
I think it's in the.
No, don't buy.
No, right by the entrance here.
There is?
I'll check. I'm leaving this here. Keep an eye on this. This is for biomedical. Yeah, no coffee.
No surprise.
Good luck. See you in class.
Yeah. קשה לעבודה, זה חלקה.
מה האירוע שם בחוץ, אתה יודע?
זהו, מסתבר שכל 50 מישהו אמר שכל פעם.
וואלה.
זה עכשיו זה גם מיליון. מה? קפה תמיד טוב, משהו מעניין.
זה משהו טוב.
טוב, בוא נתחיל לך ראש. ככה אין לך את הסחר. שנייה, ואז... שנייה, מה? הסחר זה בחיים לשתות. אוקיי, סורי.
אהבת את העיצוב החדש?
בטח, מה אתה ממשיך? אשתי אמרה לי שזה טוב, אבל ממש מפאר.
באמת?
אמרת לי, מה זה, אני משתות בקאפ? אתה שתת בקאפ? Okay, so we chose the second assignment. We would like to compare the for leading only GMOs in Israel. So, בסדר, בוא נדבר, בסדר, פילוח אוכלוסייה. כמו שראינו, נכון, יש 5 סוגים של פתרונות בעולם ה-Digital Health. בונים יכולים להסביר את הכל. IoT זה כל סנסורים רגישים, נכון? ניטור מרחוק, לא? כן, זה גם ניטור. טלמדיסין זה לא ניטור מרחוק, זה תקשורת מרחוק, נכון? VR, ואינטרופרביליטי זה יכול להעביר דאטה בין ספקים.
רגע, שאני אגיד לך למה אני חושב שזה מצוין. פעם קודמת, היו כמה שעשו גרמניה, לא התייחסתם להכל, ל-AI, ל-VR, אז אנחנו מתייחסים לזה, אני חושב שזה מעניין.
אבל אני חושב את הסודה של לקחון התיאוריות שלהם, ושפעם זה נראה ביותר, זה ל-AI?
לא.
כאילו, לא זה נראה איך אני לך, זה נראה...
או אנטי-תבנית.
טוב, פה אני מדבר, אתה מי עושה את זה?
פה אני מדבר.
כן, בוא נדבר.
זה, כן, נראה לי שזה...
תעשי את ה-IoT.
אוקיי, so
לא, תעשי ככה?
אני יכול לעשות.
לא, מה שבא לך? מה שאתה אוהב.
טוב, אני פעם ראשונה עושה את זה, אז אני בוא נראה איך אנחנו משתתפים בזה. So now we start with the IoT, so...
נכון, ואחרי זה די בעברית, אחרי זה נשמע.
בוא נעשה את זה בעברית. בגדול אני מציג פה, נציג 3 מוצרים מרכזיים שמתנתן להבין דוגמאות ל-IoT. אז בעצם המוצר הראשון זה טייטו.
זה לא שונה.
מה זה?
זה לא שונה.
זה אחד יותר יפה,
נכון?
כן,
לא זה בדיוק.
אז טייטו בעצם המוצר הראשון שאנחנו מציגים.
לא נוכל להציג את זה.
למה?
כי זה תאפשים.
מה, לתאם?
כאילו...
יש לי לתאם, יש להם.
כן?
כן, יש לי. אחד מאיתנו, למשל, יש לי לתאם.
אז מה מדע?
אז אני מציג את טייטו, טייטו שבעצם מאפשר למדוד בבית מגוון של מדדים ולשדר אותם לרופא. אז כל 4 ה-HMOs תומכים בטייטו, כל אחד בצורה קצת אחרת, אז נסתכל דוגמה לאומית. אז לאומית ממקדת את טייטו לאוכלוסייה של הילדים ושל הצעירים יותר, ולא מאפשרת את טייטו לאוכלוסייה המבוגרת, אבל באמת כל 4 הקופות שמשתמשות בטייטו שדוגמה מצוינת ל-IoT. רק נסתכל דוגמה על פלסמור, זה בעצם השירות פרסמוניטי. אנחנו רואים שכללית היא היחידה שבעצם משתמשת ומאפשרת למתמחים שלה להשתמש בפלסמור.
אתה תסביר את זה, נכון? כן. להוריד את ההגנה של נשים, יכול להגיע בכל שלב, נכון? מהחודש חמישי ושישי, שיכולה להגיע בלי הפניה מקופות חולים, למי אנשים להגיע פחות וכאן. כן, אנשים הם מרגישים. והבינו שהרבה מזה יכול להתבטא מוניטור קשה.
אוקיי.
וזה הבין לא, אתה קוראים פאזל. כמו שיקר? כל אישה. אשתה יכולה להגיד פעמיים ביום. זה לא ממש בסתם. מה שאתה לא מרגיש טוב איתה.
ודוגמה נוספת שנציג זה Urine.io, שזה בעצם סטיק שמן ביתי, שכולנו יכולים לעשות סטיק שמן בבית, אבל כאן בעצם יש לנו את האנליזה ביחס שקל, זה דבר שהוא חוסך המון למטופלים, חוסך המון לרופאים, בסופו של דבר, לא כל סטיק שקל הוא כל כך מורכב, ודורש שרופא ישקיע את זמנו בשבילו, והדבר הזה בעצם מאפשר גם קיצור, גם חיסכון של
זה נכנס לדאטאבייס של הקופה? טוב, אז טלמדיסן, דבר שאנחנו נצא להשוות בטלמדיסן, זה היכולת לשוחח עם רופאים. אז כמו שאנחנו רואים בכלל, יש להם שיטות שונות, מגיעים attitude, אז כללית מאפשרים לפגוש ככה את רופאי המיון, ככה גם עושים לאומית, טוב, ורופא אור, מכבי לעומת זאת הלכו לטריאז' וגם לרופא אור, גם ככה לאומית, וגם ככה מאוחדת, מה ההבדל? נכון, ההבדל, שכולם עושים חוק בכללית, גם את האפשרות שלך לדבר עם הפיזישן שלך מרחוק בעזרת הטלמדיסין. טוב, היכולת לשלוח ולאסוף, זה נראה לי טלמדיסין, לא? שירותי מעבדה מרחוק.
אני חושב שכן, אני חושב שכן.
נכון, נראה שזה טלמדיסין.
אבל רגע, זה שירותי מעבדה מרחוק של מה?
בסוף מגיע לך נציג, אדם משלח.
אני חושב שזה טלמדיסין.
אז זה, כל החברות עושות את זה, ונדבר על אפליקציית פיטנס. כל אחת מהחברות האלה הבינו שהכי משתלם להשקיע ברפואה מונעת, preventing medicine. כל אחת מחזיקה את האפליקציה שלה, שכוללת גישה מסובסדת למכוני כושר, גם נושאת אורח חיים בריא, ומעקב אחרי הליכה, ותוכל הנחות, בוא נמתור דרך מספיק צעדים ביום, וכו'. ואנגלית פיזיותרפי, אנחנו רואים שזה דבר שנכנס רק במאוחדת ובכללית, והיית עושים את זה בעזרת וויזקר, שזה סטארט-אפ ישראלי, לא זוכר מה הקטע שלו, ומאוחדת עושים את זה מאוחדת עם האנגלית. בוא נראה, מה היה לנו? אז יש לנו את הדבר של דיירגרס, אז אנחנו רואים כל החברות הבינו שהדרך הכי נכונה להכניס את הטלמדיסין זה כשממש המטופל צריך את זה, כי לא מטופלים לא יעשו את המעבר הזה, ולכן מנסים לעבוד על כל מיני לחצנים, רואה שזה מאוד זמין, SOS, זה מהיר, זה יעיל וזה נגיש. החסרון שאנחנו רואים, מה קשה לעשות אימוץ לבדיוק מסופשן עם הרופא המשפחה שלך, זה שצריך לעבור לכל רופא משפחה, וזה גם תמרץ לעבור בווידאו, או משקלית, או לחסות שעתיים. וכל אפליקציות בריאות האחרות שמדברים בו עולים פה 20 דקות, כדי לשלם משהו שם.
So we want to interoperability. So Klallit has its main app. So they all have different apps. בלה בלה בלה, שבעצם כל האפליקציות מאפשרות לגשת לפרקים רפואיים, לעשות כל מיני פעולות באפליקציה, בין זה זמן תורים, בין זה להסתכל על התוצאות של בדיקות, בין זה לבקש הפניות לייעוצים, נרשמים וכו', אז כל הארבע הקופות האלה מאפשרות את זה. יש בכללית את כללית קונקט, שזה מה למכבי יש את מיין מנג'מנט, שזה אפליקציה נפרדת שמאפשרת בעצם לאנשים עם מחלות כרוניות לעשות מעקב כל מיני מדדים שהם רלוונטיים למחלות שלהם, זה סוכרתיים, גלוקוז, לאנשים עם לחץ דם, בלאד פרשר, וזה בעצם מאפשר לזהות חריגות ולשתף את זה כמובן עם הצוות המטפל. בלאומית יש את הלאומית דיג'יטל מוניטורינג, שגם כן נועדה לדבר דומה לאנשים עם מחלות כרוניות, שהאיכות כזה שיש לה, יש אינטגרציה חלקית גם עם האפל הלף באפליקציה שלהם. מבחינת, עכשיו, על זה דיברנו על זה אז, ההפריד שהיה לאומית ומאוחדת, הם לא בדיבור הזה. קשה לי להאמין. לא נראה לי אני חושב שהם כולם תומכות.
זהו?
יש פה איזה סוץ.
אז למה ישאלו אותך? האם מוניטורינג זה לא IoT? יש כמו של אביש, שזה שזה רק אפליקציה למעקב?
זה אפליקציה למעקב, יש לה את האפליקציה שלהם הנפרדת, אתה יודע, של האפליקציה של הזה, ובגלל שזה בעצם האפליקציה של המטרה שלהם.
להנגיש את המידע ולא לעשות את ה...
להגיד, לנתח את המידע ולהעביר אותו לרופא, כן. אני ממש מתלבט לגבי שכולם עובדות בתחום של העסק.
לכן, אבל יש שכל נמצאות בתהליך שיאפשר. מיישמות פרויקטים מבוססים. קרדיטס משחרור דיגיטלי, מכבי, אלרגית בשיפור בית החולים לא להרגיש.
קרדיט בשביל שחרור. אוקיי, כללית ומכבי ידענו ש...
ותמיד זה לא את הסיפרה של דיגיטלי, זה כלום. לא יכול להגיד שכולם עוברות לטקניון הזה עכשיו, לא יכול להגיד שרבים כזה לא.
אז אני אעשה... אני כותב שכרגע מכבי משתמשת באלרגיות.
תגיד שהוחלט בישראל שכל מיני...
זה עוד...
Okay, so we will start with imaging, automated imaging tools. So what we see there is Israeli startup company called Zero Medical Vision, and they are collaborating with Credit and Maccabi. They are collaborating with Edo, also Israeli startup. Leumit, they did not have yet integrated any AI medical imaging. אני לא יודע מה איפה משתתפים את זה, and if we talk about AI over raw data, so we see that Credit is the most leading HMO in that field, actually in all the AI field. So they have very proactive innovation, another PPI, CPI, proactive preventive innovation. טוב, שיחוזר לך את הסיכון שלך ואתה מתי יש לך להתנדב, נכון, מספר את זה. ובאמת עושים את זה לפוליפרמסים, ומכבי היחידי שיכניס את זה לפתולוגיה. אז זה אוטומטי לגמרי, זה מציע את זה. טוב, אתה תקבל. אז אני לא עושה, אני לא עושה כבר.
כן, תעשה את זה ואז אני אעשה ככה.
אתה זוכר מה אתה אומר לי פה?
כן, כן, כן.
כן?
זה עשינו בקצת הכלי שעשינו של הפוסט דיסצ'ארג'.
כן, כן.
זה, ואז אני אצלי. תציגי את זה רגע? So now we're going to present our application example for you. So the problem is that applications is not all of its early iteration, and without
patients, like elderly, like heart failure patients, COPD, post-surgical patients. So we want us to build a structured digital follow-up embedded in the leads out that proactively monitors patients after hospital discharge using short symptoms, continuous and optional health measurements. So we thought that it should include automated check-ins at specific times after discharge. That would be 48 hours, 7 days, and 14 days post-discharge, and it can change according to the underlying diagnosis. It's an academic claim. And that recognize red flag symptoms that trigger nurse or physician review. We chose the lead because she thought it was a fun way Existing digital monitoring capabilities provide a relevant foundation for the field data, which can be a platform for our future. And focused implementation of deliver measurable impact without large-scale infrastructure changes. Our recommended implementation framework is the AAA, which, as you all remember, looking at optimizing patient experience, population health, and cost of care. So regarding the to be honest, וואו, פרגנת לי בזה.
אני כמה מלא, כמובן שעד כמה שנים, פעם שמשם שינה, אחרי זה לשכה, אם הוא היה מה זה, זה כבר, הוא עושה כאילו, אין זה לא.
כן, כן, אתה צודק.
התחלתי בשנה חמישית, ואז לשמוע אנשים בתור דוקטור, ואז אם אני יודע שאתה סטודנט, אז אנשים ביחד על המחזור,
ואז יפה,
אז כן. איפה נשים פה ברמת אפילו. עשינו כל זה, מה יש לנו? מטורף, צריך לציין שלנו את זה.
שזה היה טוב שעשינו בטבלה, ואז
and then